capacity of the battery and what type of charging inputs can be done in the batteries. Fine. Now I will be discussing about the charging profile, which I spoken in the 2 slides before. So basically how the charging profile works inside a lithium ion battery. So previously for lead acid batteries, you might have thought that just give a, if it's a 12-volt battery system, you can just give a 14 volts or 13.5 volts directly to the battery. It will automatically charged, right? Based on the constant voltage theory. But in the case of lithium ion batteries, it is not such. Generally, the lithium ion battery gets charged in a typical way in terms of constant current, constant voltage profile. So in the graph, if we see, then initially the voltage of the battery is around 2.5 or 3 volts we can consider when it is completely discharged. Now at that time, if it's around 22.5 to 3 volts, the capacity of the battery is nearly about 0% or 10% charged. Fine. Now we want to start charging the battery. So what happens from the converter or the charger? A constant current is applied. Basically, the blue line, what you can see over here, a constant current is applied to the battery till the battery voltage reaches its top level, or basically if it's a lithium ion NMC cell, then the charging voltage of that lithium ion cell is around 4.2 volts. So till the lithium ion cell achieves 4.2 volts, a constant current is applied to the lithium ion battery. So basically this is the first stage of lithium ion battery charging of constant current. Now at that time, if you observe the red line which is there, that is for the constant voltage. Fine. At that time the battery is almost charged around 70% or 65 to 70%. We can see that the battery is being charged. Now as soon as the battery voltage reaches 4.2 volts, the profile of the charging changes to constant voltage. So after that section, you will observe that voltage of the battery or the voltage of the lithium ion is always kept constant at 4.2 volts, and slowly and gradually the current starts reducing. So till the battery gets charged 100%, we will make sure that charger is on. Or the second method, generally we take it like, if the charging current goes below 3% rated, we consider that the battery has been completely charged. So at that time, we generally turn off the battery charging or switch off the battery charging. Right? So basically this charging profile, we can divide it into two parts: a constant current stage and a constant voltage stage. The first stage is the constant current stage, where maximum energy is being induced inside the charger, or basically I can say that maximum energy is stored inside the battery in the constant current mode, and in the next stage, that is the constant voltage mode, the further remaining 35 to 30% of battery gets charged. So this way every lithium ion battery charging works. This is the basic charging profile for any lithium ion batteries. Right? Now if we check about the applications, like if I say that can I use a same charger for all the applications? No, you cannot use one charger for all the applications. Basically the charger design depends on the battery specifications. So here if we see, based on battery specifications. According to lithium ion cell, I have divided, like, if one cell is in series, only single cell is there, then a lithium ion voltage, lithium ion battery voltage, nominal voltage is around 3.6 volt, and the charging voltage is around 4.2 volts. So in this condition, which are the applications like mobile phones, IoT applications, and all single cell application, charger will come in this bracket. Then if we check a 12 volt system, so a 12 volt system will be having four number of lithium ion cells in series. So the charging voltage goes up to some 16.8 volts. So all 12 volt applications, battery applications, we have to make sure that the charger charging voltage is at 16.8 volts for a lithium ion battery. Then for a 24 volt application like solar lights, LED lights, and even the BLDC motors, they run on 24 volts. So all the portable applications which take 24 volt, maybe power tools might be there and other applications, you have to make sure that you use seven number of cells, or basically uh, 24 volt application, the charging voltage would be 29.4 volts. Then if we check about the, now the transportation starts after 36 volts. So basically first transport vehicle, if I say, then it's electric bicycle. Basically all the electric bicycles, mostly like 90% of these electric bicycle, they run on 36 volt motor. So when there is a 36 volt motor, we have to keep our battery pack voltage also nearly 36 volt. So generally 10 cells are put in series in this lithium ion. This lithium ion series combination, if we check, then 10 cells are in put series, and the charging voltage of it is around 4.2. So basically 10 multiplied by 4.2 volt of each cell becomes 42 volts. So all the chargers for an electric bicycle would be designed at 42 volt charging voltage. Current may be different, like current depends on how much capacity of battery we are using. That depends on manufacturer to manufacturer. Some might be using 10 ampere capacity, some other may be using 15 ampere, 20 ampere, like that. So basically for electric vehicles, the starting point of the voltages is 42 volts. Then moving ahead, that there is 48 volt system, 72 volt system, 96 volt system. These three domains, these three voltage domains are majorly will be used in the complete electric vehicle ecosystem in India. Because if we say the major transportation vehicles in India, then it's electric bike, electric auto rickshaw, electric motorbikes, and motorcycles. Then others are electric golf carts, and you might be seeing in malls there are electric cars are available. Mostly all these vehicles, they lie in these three voltage domains, that is 48 volt system, 72 volt system, or 96 volt system. So for them, the charger design would be at for 58.8 volts, 84 volts, and 113.4 volts. These play a major important role. And for electric cars, electric buses, they generally are above 100 volts. They might, some vehicles might be using 200 volts, 400 volts, 450 volts. So that is currently still not standardized about the voltages of each vehicle. But each and every OEMs, they are keeping their own individual charging methods or charging voltages. So that depends on vehicle to vehicle, right? So this is a wide application range of the electric vehicle charging we can think of. Now, in this slide, I will be discussing about the basic charging design, like what are the components which are available in a electric charger. So if you open a charger, electric vehicle charger, then which are the uh, components would be there and which are the topologies everyone might have used in their application. A brief idea will be taking over here. So basically, if I take that the input is AC single phase 230 volt for our Indian application, then the charger, uh, first of all, basically how the charger would, like, 230 would be the incoming volt, AC incoming volt, but you want to charge a battery, for example, of 48 volt DC. Fine. So what steps you need to do first? First of all, your voltage is AC, right? So you have to convert that AC voltage into DC voltage through a rectifier, basically a diode rectifier. We generally we use a diode full wave diode rectifier for converting AC to DC. Then comes a PFC stage. Now, what is this PFC? Basically, it's power factor correction unit or power factor correction circuit. Now, why do we require a power factor correction? Like, your load might be anything. It might be inductive load or a resistive load or a capacitive load. Fine. So if it's a resistive load, then from the if it's a resistive load, then generally the voltage and current would always be in synchronous. Like there won't be any phase difference between voltage and current. But if you are having a load, might be a motor or maybe a battery, might be inductive load or a capacitive load, then voltage and current won't be in their phases. Means that they won't be synchronous in their phases. There would always be lagging in their phase or leading in their phase. And due to this lagging and leading in their phase, the active power which is actually going to the battery would be reduced. So for example, you might be giving 100 watts of power at the incoming, but it is possible that at the battery or at the DC stage you might be getting only 80% of the usable power, and over to that there would be losses in the efficiency, there would be losses in the components, heat losses would be there. So the work of this PFC is to make sure that it keeps voltage and current both in one phase. So basically the phases of currents and voltages should be in line. That is the work of power factor correction, and that this helps to actually improve the efficiency of the charger. It helps to reduce the harmonics of the charger, and it is a mandatory from the electricity supply distribution companies that we have to make sure that we keep our power factor above a certain level. So that's why it is a very important part inside a electric vehicle charger. Then comes the DC to DC section. So basically up to this we have converted our AC voltage to the DC voltage with power factor correction. So at the input of this DC section we have a proper DC voltage. Now this DC section would be a isolated one. Generally all the electric vehicle chargers are isolated chargers. Like isolation means that the input side and the output side, they are isolated majorly with transformers, or basically we can say they are magnetically isolated systems. So at the input of the this DC stage which are there, Then there comes various types of topologies. Right, topologies like there is push pull topology, half bridge topology, full bridge topology. In the full bridge topology also there is uh, phase shift full bridge LLC type of converter. So based on our applications and requirements, we have to make sure which topology will be best suit for us based on the precision level, efficiency level, cost perspective. Everything we have to consider. Now, after this DC-DC section, so basically this DC-DC section will convert the higher voltage, because at the input there would be around 270 volts, or if it's made boost converter is used with the PFC, then generally the PFC output is around 390 volts to 400 volts. Fine. So to convert that 400 volts to 48 volt, we need a DC-DC conversion with transformer. So basically the transformer will change the voltage levels, and the switching of this, because basically in this DC-DC converters there are MOSFET switches which are switching according to the algorithms. So that switching process occurs to make sure we get output voltage 48. But prior to the output voltage, there would be output filters which will actually smoothen the waveforms of the voltage and current to make sure there is smooth uh, voltage going outside the charger. So these output filters are generally used. Now in the bottom side, you see the controller. So basically a microcontroller or specific application specific ICs are there for PFC conversion, then for DC-DC application are used. So either you can use a microcontroller for it, or you can use specific ICs for it for their specific controls. But we have to use a small microcontroller for our communication purpose, like CAN communication, because in automotive domain, a CAN communication is must for communicating either with the battery pack or with the vehicle control unit or the motor control unit. So based on the application and based on the architecture, we have to communicate with different components. Then we have to continuously have feedbacks of voltages, currents, temperatures. So we have to keep sensors for sensing this all these parameters, and based on that parameters, algorithms are put to make sure the charging system works properly, because here only we have to uh, design our algorithm for the constant current, constant voltage system. So this is a typical block diagram of a charging system. I can suggest you. So in detail, if we want to go, then for each and every component, there is a huge amount of theory we need to study. We have to do practicals for designing it. Right? Now, basic features of a battery charger, if we discuss, then battery charger should be compatible with all the types of batteries, because as a charger manufacturer, I don't know like which type of batteries you have used. You might have used Panasonic, some other might have used Samsung batteries, some third person might have used BYD batteries or A123 system batteries. Fine. So, and all these batteries, they might be having different battery chemistries, lithium ion chemistries. So based on the chemistries, our charger should be compatible. So that type of charger we should make it. Then it should be highly efficient, compact in size. It should be robust and reliable. Operation should be there. Robust means basically it would be used by the illiterate people. So basically illiterate in terms of the electronics of the charger. Like say suppose your father or your uncle or your aunt, they are using this charger, They might not be the electronic engineers or the electric. And for vehicles are or the chargers are very much robust in nature. That it should be robust in all types of temperature levels, in all weather conditions, by all the type of users. Right? Then and also it should be safe use for the individuals. Then we should have protection based on voltage, current, and temperatures to make sure the safety of the charger and safety of the battery. Then we definitely should have CAN communication for communicating with the vehicle controller. Also, there should be indicators for various faults. Like suppose there is some fault occurring inside the charger, then indication of the fault should be made so that the operator or the service person can easily repair your charger, or it should be easily repairable. So and even if it's not repairable, one should understand that there is some issue, specific issue with the charger. And there are multiple features based on the complexity you want to put, but these are the basic uh, charger, battery charger features. Right? Now, the topologies of the charger, like in the block diagram section I discussed with you, like there is PFC section, then the DC-DC section is there. So like that, if I want to divide the charging systems based on their topologies, which we can use it for our different applications, then this chart is, this table is very important. So first of all, on the top we have AC to DC. Means every charger will require this portion AC to DC. Means that it will convert the AC 240 volt AC or 415 AC supply into DC voltage. That can be done by two methods: diode bridge rectifier or active rectification. So basically it's type of rectification, which means that it converts AC voltage into DC flat voltage. Now after rectification has been performed, we have to perform power factor correction unit. So basically we have to make sure that the voltage and currents are in phase, and make sure the power factor of our charger is nearly about 1. It won't be 1, but around zero point 0.9 or 0.95, 0.99. We have to make sure that we achieve the best power factor correction, because eventually it will improve on the efficiency, it will improve on the harmonics of the uh, electric signals, and it will make sure that we are bound to the electricity distribution systems. Fine. Now once we have done the power factor correction, we are having a proper DC voltage. It will be a higher voltage, around 390 to 400 volts. From that stage, we have to convert our battery, or we have to convert the voltage of the battery charger according to our application, which we discussed. It may be a 48 volt system, a 96 volt system, 12 volt system, or 400 volt system, 650 volt system, right? So based on the topologies over here, on power levels I have differentiated. Generally, if you want to design a charger up to 100 watts or like that, generally we go for flyback converters for DC to DC conversion. Then for a bit higher power level, we go with the forward converters. Then above that, push pull converters are there. Then half bridge converters are there. Full bridge converters are there. And finally the phase shift full bridge converter. So based on our application level, based on our power level. So if I give you an example, that mostly all the electric vehicle autos or the e-rickshaws, they either charge with 800 watts to 1000 watts or up to 1500 watts based on the battery capacity. All the electric bicycles, they have a charger of 300 watts to 400 watts. That is like uniform across all the types, mostly all the types of vehicles. But if you are talking about the fast chargers, then for fast chargers you will be requiring phase shift full bridge chargers, because they are specifically used for high power applications. And also for mid power applications you can go for full bridge LLC type of charging topology. Fine. So these are basic topologies. So in, if you want to learn each and every topology in detail, then you have to actually go in depth for each and every topology and learn like how each and every topology works, how the PCB designing of each and every topology works, then component level designing we can do on it. Right. So this is a preliminary overview of the charging topology. Right? So this is like an introduction to electric vehicle charging systems, from its trending, then types of chargers, then infrastructure, various EV infrastructure. In that, what are the types of charging methods, levels of charging we talked about. Then the charging profile was introduced. Then applications of the chargers based on the end user application we checked out. And finally, we learned about the various topologies of the charging, like the DC-DC topologies and AC to DC topologies, and introduction was given to